slide number 25 of chapter 1, reverse recovery time for a diode when you switch from a forward bias to reverse bias state. We talked about this in our last class, and that's when I stopped. Let's move on to the next topic. Did you have any questions from the previous class?
I don't
Seems
have.
okay. Seems like there are no student questions yet. Switching to full screen. So let's move on to slide 26. I intend to teach at least until slide 41 today. We will have a few practice problems. Some of the practice problems are examples from the textbook, and some problems I try to just draw simple diode circuits to test your understanding of output voltage, the on and off stage, etc. Normally I go by the student list I have, so for each problem I'll call the students on my list. The first problem, first student, second problem, second student. So this way I try to work through the whole list so all students can participate. There is no penalty for giving me the wrong answer, but you should participate. So what are we looking at now? Diode spec sheets. Every device component, they come with a spec sheet when you purchase from a manufacturer. These are some of the information that should come on all diode data sheets because these are important. The first one, forward voltage. So the forward bias voltage, at what voltage it will turn on, usually given at specified temperature and also the current level. The temperature we use room temperature typically taken as 25 degrees Celsius. Spec number 2, maximum forward current at a given temperature. A diode cannot handle infinite current. It has some capacity. If you exceed that capacity, you can damage it. So when you design the circuit and use the diode with the rest of the circuit, you have to be mindful of that. The next one, usually on the spec sheet, is the reverse saturation current, sometimes written as IR on the spec sheet. In this class, I was saying I sub S, but it's the reverse saturation current, also specified at a voltage and temperature. Number 4 is quite important. The PIV, PRV. PIV is peak inverse voltage, or some people say PRV, peak reverse voltage, or VBR, breakdown voltage. In the reverse bias, you cannot give infinity voltage, infinity minus voltage. There's a limit. If you exceed that limit, there will be a lot of current in the reverse. The diode will break down. It's called PIV. Number 5 talks about maximum power dissipation, usually given in milliwatts for small devices. So how much heat it can handle. The output voltage and output current, when you multiply voltage and current, you get an output power. This power is, you can see when you turn on your computer or you use your cell phone, whatever it is, every time you're using for long, it heats up because it's passing voltage and current. Every device has a limit. And from my experience, I can tell that the biggest enemy of any device, laptop, cell phone, or anything, is the heat. That's why when I take the class, I try to keep the room temperature very cool. I already had to change one battery for my laptop. Capacitance levels, sometimes they are given on the spec sheets. Number 7, reverse recovery time, very important spec. This should be given on all diode spec sheets. And then number 8, this is a standard information for all components, diode, amplifier, everything. What's the operating temperature range? Usually, I think it's from, what is it, 5 Celsius to 35 or 40 Celsius, maybe 35 Celsius for consumer electronics. For medical devices and military grade devices, they have extreme temperature range. Maybe they operate at minus temperature, minus 40 or minus 50, all the way to plus 50 Celsius. But those devices are high spec. Regular consumer devices, they are not made for that. The symbol for diode, if you want to look inside a circuit, P and N joined, anode cathode. When you draw in the circuit, it's like a triangle, upside down triangle, and the bottom part is the cathode, this line. If you try to find a physical diode in the lab, it might look like any of these, different construction. Anode sometimes is marked with the letter A, and cathode is marked with the letter K, or a dot or a ring, a circular ring. K, because even though the spelling is C, starts with a C, C-A-T-H-O-D-E. When you pronounce it, it sounds like the K sound. That's why abbreviated as K. If you want to check whether or not a diode is functioning properly, there are different ways of doing that in a lab, or even using your own hobby kit. If you have, you can have a diode checker, ohm meter, or a curve tracer. If you check a diode with a diode checker, most of the multimeters we have, digital multimeters, it has a diode checking function. You have to twist the knob, put it in the diode checking mode, and if a gallium arsenide diode is normally functioning, if you put the plus probe on the anode and the minus probe of the multimeter on the cathode, you'll see a voltage 1.2 volts. Similarly, for a working silicon diode, it will show on the multimeter 0.7, and for germanium it will be 0.3 volts around. You want to check an ohm meter. So if you don't have the diode checking mode, and you want to use the multimeter as an ohm meter, or you have an ohm meter, set it to a low range scale. If you put the red probe on the anode and black probe, which is the ground probe, on the cathode side, this is in a forward bias manner, it should show a relatively low resistance, as if the current is passing. If you reverse the probe, the red probe is now on the cathode and the black probe is on the anode. The ohm meter will show a high resistance value. It is as if current is not passing and there seems to be an open circuit, which is equivalent to a high resistance or even infinite resistance. Curve tracer is a special type of equipment in the lab. If you put any device there, maybe a diode or an amplifier like JFET, which we'll study after the diode, it should show you the characteristic curve of that device. So what are you looking now on the screen? What does it show? If you see this blue curve, what does it remind you of? Nothing happens until about 0.6 volt, and then at 0.7 volt it is a lot of current. This, you can say, this is a silicon diode being put on the curve tracer. So you can look at the curve on the curve tracer, and then you can compare the values that are shown on the curve tracer, compare it with the data sheet. If it is okay, then the device is okay. If it's not, you might have some malfunction. We were talking mostly about the regular diode in our first class. There are several other types of diode, which is all part of diode family. The common ones are Zener diodes. We will do Zener diode problem at the end of this chapter. LED is also a diode. They emit light. Diode arrays are combination of multiple diodes. Can everyone see the slide Zener diode?
Yes, Sajed.
So look very carefully at the symbol. A normal diode, the triangle should be up, the horizontal line should be down, and plus and minus. That is, we call the forward biasing. If you have a Zener diode, it's a special type which operates in reverse bias. So the cathode is up, anode is down, and this is not a straight line. This looks like a curved Z or S, not a straight line. Once the diode is operating, if you try to measure the voltage across the diode, it is plus and minus, not minus and plus, even though cathode is on top, anode is at the bottom. This is a special case. Once the diode turns on, you still read the voltage like plus minus, but you have to connect in opposite way. And IZ is the Zener current. Once the Zener turns on, there are some conditions which need to be fulfilled. IZ is the Zener current when it turns on. Zener diode is also known as voltage regulator because each Zener diode has its own voltage. Depends on the model. You want to buy a 2-volt Zener diode, it will give you only 2 volt across when it's turned on. If you want to buy a 12 volt or 20 volt Zener diode, it's up to you. It depends on your need. What do you need in the circuit? The voltage is fixed, that's why it is regulated. It's called, also known as a voltage regulator. Typically, you can find in the market the Zener voltage ratings will be between 1.8 to 200 volt. You can go up to that high, yes. LED is a light emitting diode. When you forward bias, which means you apply the proper polarity and sufficient voltage, it will conduct the current, and when it conducts the current, it will give you the light. The light may or may not be seen by your eye, because in our human eye, we cannot see all frequencies. The ones we can see are called lights from visible wavelength or spectrum. The ones we cannot see, but the light is still there, infrared. So my remote control right now for the air conditioning, at the end, there is an LED, it emits some light, but I cannot see. The humans cannot see. Light is electromagnetic wave. Based on the definition of light, it is electromagnetic radiation. So in that case, radio wave is also a light. Wi-Fi is a light. Radar, microwave, those are also light by scientific definition. You just don't see it. The symbol for LED is a bit different. As you can see, you have a regular diode symbol, but next to the diode symbol, you have a pair of curved arrows. This is the symbol of LED. I just briefly mentioned about diode arrays. If you combine multiple diodes together in a package, we call it array. Array is a collection of things. You can do it by 2 ways. You can take all the anodes together. Let me try to draw. All the anodes joined together. I'm drawing a yellow area. Do you see that? So they have a common connection at the anode, and cathodes are all individual input pins or output pins. You can also take all the cathodes together and join them. This is called a common cathode connection. And the anodes are open for you to take input or output, whatever that it is. The diode array comes in usually a package which will look like an IC, integrated circuit. Just like this one, this thing. You can have so many types of configuration for a diode. What we start today mainly is diode applications and circuit analysis. Like I said before, for this course, you should have basic knowledge of circuit analysis. Not very complicated, but definitely need to know the basics. And I believe physics 2 is also a prerequisite. Now on slide 37, I hope everyone can see it. We start with the load line analysis. Can you see? Can you see the load line analysis?
Yes.
Yes.
Okay.
Okay.
Please let me mute one of the student because there is a background noise. But if you need to speak up, then you can unmute yourself or request me. I think the noise is gone. Is there a background noise from my side? I think not.
The background is a little bit for me.
Okay. Do you have any noise from my side or no?
Not that loud, Acha, but
Okay. There's a fan running. I just try to move. Load line analysis is the beginning of the techniques that we use to analyze circuit. The picture shows you a graph which is ID versus VD. ID is here. As I circle, it is the y-axis, the diode current. VD is the diode forward voltage. Which do you recognize the blue curve? What is the blue curve? The blue curve, we call it the characteristic curve. It is the nature of the device. It is not going to change. Different devices have different characteristic curves. And then you see a dark straight line. One is at E. One extreme of the line is on the x-axis. We call it point E. This is a voltage value. The other extreme of this line is at the voltage divided by some resistance. Where the straight line intersects the characteristic graph, this point we call it the Q point or operating point. Q comes from the word quiescent. At this point, if you project a line on the voltage axis, you intersect right here. This is VDQ, which means this is the diode voltage at its operating point. Then similarly, you project another line which should intersect the current axis. This point is IDQ or ID sub Q. This is the current value, the current that is flowing through the diode at the operating point. So how do we get the straight line? The straight line can be changed, so the Q point will also change. Maybe we can bring the straight line, the E to the left, and Q point will go down. Then you will have a different voltage and different operating current. Where is this load line coming from? The blue line is coming from the characteristic of the device itself, but the load line will be decided by the network or by the circuit in which you put the diode. In order to find the load line, we should actually look at a circuit. Before I go a bit further, also appreciate that when the diode voltage equals E, what is the current? At this point, let me put an arrow. What is the current at VD equals E? Anyone?
Zero current.
Zero current. Very good. And then look at the other extreme points. When the current equals E over R, what is the voltage? Voltage is?
Zero.
Zero voltage. So you have two extreme cases. At one point you have maximum voltage, zero current. The other point you have a maximum current and 0 volt. Just remember these two for now. We will see it in action. Here is a simple series circuit. E is for the electromotive force, I believe. Sometimes they put V, sometimes E. This is a battery symbol, plus, minus. So if the battery doesn't connect to any load, the open terminal voltage is known as the electromotive force, EMF. The unit is still volt. This diode is showing silicon Si under its picture. So once it turns on, the voltage will be 0.7 volt once it turns on. If you put a battery voltage of 0.2, it will not turn on. You should have sufficient amount. Now, if it was germanium, it would say 0.3. What happens if in the problem I don't give anything? I don't give the material. What voltage should you take? In that case, it is called an ideal diode. What is the voltage? When the diode is conducting, is it open circuit or closed switch? It's a closed switch. Short circuit voltage is 0. So the voltage across will be 0 if it's an ideal diode. Now let's solve this loop. Kirchhoff's voltage law. What is the equation? E, can you tell the equation? E minus V of D. This is your output voltage, V of R or V sub R. Minus VR equals what? What is the Kirchhoff voltage law? In this loop?
Equals 0.
Equals 0. Yes. The total voltage around a single loop is 0. Or you can say voltage rise equals voltage drop. E is voltage rising. E equals VD plus VR. Voltage drop is VD and VR. What is VR then from this equation? If you put VR on the right hand side, it is E minus VD, which you can see on the slide. What is the diode current ID? In a single loop circuit like this, the current is very common, same current. ID, the diode current which is flowing is the same as the current that is flowing through the resistor. ID equals IR. So what is VR? VR is ID times R or IR times R, Ohm's law. You can see here. VR equals I times R. Now I think this slide is a bit wrong. It says reverse bias, but it is giving you a forward bias diode. From this equation, you can see E minus VD minus VR is 0. Later on, we'll do further analysis. So if you move VD to the right hand side, in this equation, notice, move VD to the right hand side. VD equals E minus VR. Everyone understands this point? VD equals E minus VR. Now tell me, when the current is 0, in this equation, what is VD? E, instead of VR, I can say I times R equals VD. This is another representation of this equation. Tell me now, when the current is 0, what is VD?
VD equals E.
VD equals E. When the current is 0, it means, why the current will be 0? Because it's an open circuit. So if you have an open circuit, if you put a probe on this point, you will just sense this E. VD will be E. Come back here. When the current is 0, you see VD equals E. Now, if VD equals 0 in this equation, what is current I? Now I say VD is 0. short. Now your equation becomes E minus IR equals 0. Therefore, E equals I times R, and therefore I equals E divided by R. That's the other extreme point. When BD is 0, I equals E over R. These two extreme points, when you find on the graph, you join, intersects with the diode characteristic curve, then you can find the actual current. You can find the operating point, then you can find the actual current and actual voltage. That's why you have to do the load line analysis. Now, let me correct this thing a bit. For a reverse bias, I think the symbol should be like this. This is a mistake from the publisher of the slide. So let me try to draw and cover this thing. In a reverse bias, is the loop open or closed? Is the switch open or closed? That's my question. Now you have plus voltage. This is the negative terminal of the diode. Ignore the black symbol because it's wrong. This is the negative terminal cathode. This is the positive terminal anode. Is the diode on or off? In reverse.
It should be off.
It is off. When it is off, it is like an open switch. This circuit is open. When the switch is open, no current can flow. That's why in this example, in this slide, it says ID or IR 0 amp. If ID is 0, IR is also 0. They're the same current. Is there a voltage drop across VR? No. Ohm's law, VR equals I times R. If I is 0, VR is also 0. BD will be same as E. We showed this in the load line. When ID is 0, BD equals E. Because if you put a probe at this point across the open switch, you are not sensing the voltage drop. You are just sensing, the probe is sensing from the source of the voltage source. So in the reverse bias, you have voltage, you don't have regular current. Saturation current you cannot measure with your regular tools. That is in micro, nano, or picoamperes. We are talking about the main current. Main current is 0. Any questions about that one? No questions? We're still in the simple circuit. I just received a message on my chat screen. Okay.
Ajahn,
Yes.
if it plus same direction at the
Which
vector,
one?
this one, how do you know which one is closed, which one is open, Ajahn?
Okay, first of all, in this slide, there is a mistake. Where is the mistake? This picture is a mistake. This one is putting a diode in forward bias, but this is talking about reverse bias. So forget about the diode symbol. The diode symbol is like this. When diode is like this is the anode, which is the plus terminal. This is the cathode. Now you see, if you need to turn on the diode, the anode should receive a plus voltage, but the minus is connected to the anode. The cathode should receive a minus polarity, but plus polarity is connected to the cathode. That's why you know that it is not turned on. It has to be off. That's how you know it. When it's off, switch is open. So does it answer your question?
I'm just confused, Ajahn. So when minus anode connect to plus anode, which field it will be closed, right?
Anode, if connects to positive voltage, and cathode connects to negative voltage, it will be on. Now you see the cathode is connected to positive polarity. And if you look at the rest of the loop, anode is connected to negative polarity, it will not work. This condition is a reverse bias condition. If you want to turn it on counterclockwise, you have to put plus here, minus here.
Okay, ครับอาจารย์ thank you ครับ
We will have practice today. I will show you some other practice problems. What if you have a parallel diode? My next topic is do the same analysis with the parallel diode. As you can see, there are 3 loops going on here. The first 2 are closed loop, and output, if you try to measure or put a load, you'll have an output voltage. It's a silicon diode, so when it's turned on, diode voltage is 0.7 volt. We have a voltage source 10 volt DC. In between the voltage source and the first node, you have a diode D1, then you have another parallel diode D2. Both diodes are from the same material, so when they turn on, VD1 and VD2, they're equal, 0.7 volt. What is the output voltage in this circuit? You are measuring the output voltage here, plus, minus, and it is measuring across the parallel node. Therefore, the output voltage will be also 0.7 volt. What is VR? VR is here, plus, minus VR. E minus 0.7, because on the left-hand loop, if you just look at the left-hand loop and apply Kirchhoff voltage law, what do you get? 10 minus VR minus 0.7 equals 0. So how much is VR? 10 minus 0.7 is 9.3 volts. Voltage across the resistor is 9.3. How are you going to find the main current, which is IR or I1? Voltage across the resistor divided by the resistance. 10 minus 0.7 divided by, it is 0.33 kilo ohm, which means 330 ohm. This is 28 milliamp. When the 28 milliamp current comes to this node, what happens? Kirchhoff's current law. A part goes to diode 1, the other part splits to diode 2. And then this current comes at the bottom. This current flows clockwise. They join and back again in the circuit. Everyone remembers Kirchhoff's current law? Current coming inside the junction must equal to current going away from the junction. So if you have 28 milliamp current coming in and 2 diodes are exactly the same, symmetrical diode, they should be divided equally, 14 and 14. Each current is 14 milliamp. So do you understand up to this part? Any questions for me? Like I said, very basic circuit analysis, nothing complicated. Any questions?
No, John.
No questions. Okay, this is topic for the, like, maybe not today or today, at the end of today. Now, I'd like to switch the screen and bring you to a place where we can do some practice. So your Teams page now, class notebook. First, start with the resistance determination. I hope you can all see. I will make the screen larger. the picture larger. Can everyone see now?
Yes, sir.
I pick 3 students for the 3 parts, part A, B, C. Balang, are you here? Mr. Balang, first student on the student list. I see you online. Please respond, Balang. Thirawut,
ครับอาจารย์
is it Thirawut or Thirawat?
ธีรวุฒิครับ
Thirawut. Since Balang is not responding, Thirawut gonna go to part number 1. We ask you to do the DC resistance level. So find out at 2 milliamp of current, what is the DC resistance of this diode? You see the current axis and the voltage axis at 2 milliamp. What is the DC resistance? Thirawut? Two milliamp. What is the corresponding voltage at 2 milliamp?
0.5 ครับ
Okay, so please give us the resistance value at this point. DC resistance. What's the formula for resistance? Ohm's law. Did you calculate? .5 volt divided by 2 milliamp. What will you get?
0.25 ครับ
Is it? The voltage is 0.5. The current is 2 milliamp. What is 2 milliamp? 0.002 ampere. You have to change to voltage in ampere. 250 ohm, not 0.25. It's 250. Is Napatra here?
Yes.
Okay, for you, Napatra, when the diode current is now 20 milliamp, what is the resistance? Look at the diagram. Did you calculate?
40 ohms.
40 ohms. Correct answer is 40 ohms. At 20 milliampere, 40 ohms. What do you see? 2 milliampere, small current, this amount of voltage, which means there's not a lot of current, also indicates the resistance is high. When you pass the voltage value, which will pass through the depletion region, remember the wall in the middle of P and N material, it has enough energy, which means less resistance, a lot of current. Is Pakon here? Pakon? Mr. Pakon. 601 1555? I see him online. Can you respond? Let's go back to Balang. Balang, can you hear now? Those who does not participate loses the mark for participation. Rajay,
Yes, Ajahn.
Rajay, you're here?
Yes, I'm here, Ajahn.
Okay, for you part C, Rajay. Now, when VD is negative 10 volt, what is the resistance?
Okay, Ajahn.
Wait, is that micro?
Microampere, yes.
Okay. Wait, micro is -6, right?
Negative 6.
Okay.
Micro or milli, Ajahn?
It is microamp. This current is microamp, 1 microamp. I get a value which is large.
What do you get, teacher?
I get 7 zeros after 1. Minus 10 volt divided by minus 1 microamp.
Okay.
Is it 1 times 10 power 7?
Yeah, negative. Nah, I get the negative.
You divide a negative voltage by a negative current, the negative cancels out.
Oh, I didn't see negative. Oops.
Or it is 10 mega ohm actually. After 10 you have 6. The current is negative, voltage is negative. It's a negative current on the negative y-axis. It's 10 mega ohm. Huge resistance, which is like an open circuit. And that is quite correct because the resistance is so high, there is not going to be a lot of current. There's going to be only small reverse saturation current. That is because of the minority carrier flow, which I explained in the last class. This example is proving that in the reverse bias region, the diode acts like an open circuit, ideally. 10 mega ohm is almost like an open circuit. We cannot find infinity resistance in real life. 10 mega ohm is kind of like an infinite resistance, a real application of infinite resistor. And we have some other examples. Example 2.4, try to find voltage and current. I think that is the example. So I present to you in front of your screen now. How do I get rid of this? Okay. Is Chonikan now in the class?
Yes ค่ะอาจารย์
Okay. For you, I would like you to tell me what is VD. So part A for Chonikan, VD. Find VD. Michelle, are you here?
Yes อาจารย์
For Michelle, you will do the part B that I'm drawing. You tell me what is the VR. And part C will be for field. Field is here.
Yes, sir.
Find ID or IR, whatever the current is in the loop. One thing to make clear, just because I ask these 3 students, it does not mean that the rest of the class can sit or don't do anything. You are also free to do. Sometimes your friend needs help, If you find the answer already, I allow you, you can help your friend. But everyone work together. This is just to ensure everyone is participating. Before you start working on the problem, I will tell you the first step that you have to do. Once you have a circuit with the diode, please look at the surrounding of the diode. Look what is around the diode, what is coming in, what is going out, what is the polarity, and make decision whether or not the diode is on or off. After that, you will solve the problem. So back to Chonikan. Do you think the diode here is on or off?
on off ค่ะอาจารย์
On? Off? Why is it off? Should it be off?
I'm not sure I join the class late ค่ะ I don't understand some point ค่ะอาจารย์
Okay. So look at VD. This is a silicon diode. How much volt you need to turn on silicon diode? You need at least 0.7.
0.7.
Yeah. So look where it is connected. What voltage is coming in? 8 volt is directly coming in here. Definitely it is more than 0.7. It will turn on. And polarity is plus. This is plus side. This one is minus side. It is forward bias now. Once the voltage, the diode is turned on, the circuit loop is closed. What will be the VD across the silicon diode now? For Chonikan who joined late, once the silicon diode turned on, you have to write VD is 0.7 volts. Do not forget the unit. When you give me an answer without the unit, I cut mark in the exam. Not all, but some. Some quantities, they don't have units, some they have unit. Make sure in the final answer you give me the unit. Michelle, since I already give you 0.7 volt for VD, Michelle, now tell me what is VR? Which circuit rule will you use to find VR? Kirchhoff's voltage law. According to Kirchhoff's voltage law, what is VR then? Michelle?
Yes อาจารย์
Can you find VR?
No ค่ะ
No? Anyone else wants to help Michelle? What is VR?
7.3.
7.3 is correct answer. 7.3 volt. How did you get that? This is the loop. Around the loop, the total voltage is 0. So 8 minus VD minus VR equals 0. What is VR then? 8 minus VD. 8 minus 0.7 is 7.3 volts. Phil is doing IR. Did you find IR, Phil?
3.318 milliamps or 3.32 milliamps.
3.32 milliamps, yes. How did he do it? I'm guessing you took VR divided by R.
Yes.
Ohm's law. In this case, it's correct because there's nothing in between. So if you take the voltage of R and divide by the R, you directly get the current. And IR is same as ID. It's one current, there is no branching. You take 7.3 divided by 2200 ohm, which is 2.2 kilo ohm. I get 3.318 milliamp or 3.32. We can call it 3.32 milliamp. Small m, capital A. If you write big M, it becomes mega. That will be a mistake. There's another example, I believe, for the circuit, example 2.9, which I also wanted to do for today's class. Looks scary, isn't it? But sometimes you may see circuit which is like this. Let's zoom on to this circuit first. Make it large. Now you see what's going on. You have a first voltage source. There are two voltage sources here. The first voltage source, which is a DC, it is coming like this. 10 volt DC. Then you have a resistor R1. The voltage across resistor R1 is V1. After that, you have a silicon diode. This side, you can see it is anode here, cathode, so plus minus. I can write here plus minus. And then at this branch, you have second resistor R2, which is not connected to the ground, is connected to a second voltage source with the polarity -5. The voltage across R2 is given as V2, plus minus, like this. Means you put the plus probe here and minus probe. You might get a negative voltage, but the probe position is like this. Red probe is plus, the black probe is minus, as if you are measuring in the lab. Then V out is taken at this point. So if you put a V out probe, the plus probe is right here. Minus probe maybe with respect to the ground or here. How do you solve this kind of circuit? First of all, what I told you is you must determine whether the diode is on or off. If the diode, you see, you have to look at the surrounding. There are plus volts on the left side, minus volt, but it may be the case that this side is net positive, this side is net negative. Or it might be the case that the anode side becomes net negative, the cathode side becomes net positive. What happens? If anode side is net negative, this is net positive, the diode does not turn on. The loop is not complete, there is no current flowing. So everything will be zero except this voltage, V1. The current will be zero, output current, output voltage will be zero. If the diode is on, if you determine that the diode is on, we equivalent to a closed switch, and it is written silicon, so this will be 0.7 volt when it turns on. To make things simple, we have to redraw this kind of circuit. Here, E, plus minus 10 volt, the minus 1 is on the ground. This is the ground of the first DC source. Then you have the resistor, we can call plus, because it is going clockwise. Current is going from plus to minus. We use the conventional current flow clockwise, plus minus V1. And then this is a diode. It's an internal resistance, like a small resistor. We have learned about this, very small, maybe 10 ohm, 2 ohm to 10 ohm, negligible. Then where is the node? This node connects with the second resistor and then another DC source, but it is -5, so minus polarity on top, plus polarity on the bottom with the ground. Now does it look simple? Now you tell me, do you think the diode is on or off? Is the diode on or off? What's your idea?
The diode is on.
The diode is on. I think it's the correct answer. See what is going on here. Diode is connected like this, anode and cathode. So here is plus, here is minus. You're gonna get 10 volt. There is going to be some voltage drop here. 10 minus V1. At this point, the voltage on the anode side is 10 volt minus V1, whatever that is, but definitely looks like it will be a positive volt, much larger than 0.7. On the negative side, you see there's a negative polarity joined with the negative side. Fair to assume that this is negative, this is positive, so the diode is now forward biased, it is on. We can now solve for the whole loop. We can say E1. Now let's draw the loop. So the loop is active. This is our loop KVL. What formula is the KVL in this circuit? E1. I start with the outer side, so I start with plus E1, then E1 minus V1 minus 0.7 because it is on, right? Plus minus V2 plus E2 equals 0. So E1 minus V1 minus 0.7, which is silicon, minus V2. Yes, plus minus, correct. Now, is it plus or minus E2? The outer sign is plus. Plus E2 equals 0. Does everyone get up to this point? This is the KVL equation of this circuit. Does everyone understand up to this? Since the loop is flowing clockwise, this is plus and this is minus sign. Then you have a battery. The minus is here. And this is the minus sign of the battery. This is the plus sign. Any questions so far? Can I move on to the next?
Could you please explain it again?
Which part?
This equation.
The equation comes from Kirchhoff's voltage law. The total voltage around a loop is 0. The loop is drawn in green curve. The green arrow curve that I drew, it is the loop from here to here because you have a common ground. That's why I told you that you need to know basic circuit theory to understand this course. So you do the loop equation. I can start with negative E1 on the bottom side. So it will be minus E1 plus V1 plus 0.7 plus V2 minus 5 equals 0. It is the same thing because right hand side is 0. If you now multiply the left hand side with a minus sign, 0 multiplied by minus sign is still 0. But I started from the outer. The arrows goes from bottom to the right, counterclockwise. In the flow path, I took the outer symbol. If you take the outer symbol, you have to take the outer symbol for everything in your path. If you start with the first symbol, you have to take the first symbol for every element. So E1, second one, minus V1 minus, for silicon diode is 0.7, minus V2. V2 is across the resistor R2. So let me make it clear. V2 is not V out. V2 is just R2, voltage across R2. And then what is the second symbol of this battery? Minus plus. So plus 5 equals 0. Do we know V1, V2? We don't know yet. We can find out. What is V1 according to Ohm's law? I times R1, isn't it? In this loop, is there one current or different currents? Anyone? Is it one current or different current? Same
Two
current.
currents. Oh,
Same currents. V out is just probing. You don't have a loop there. In the left-hand loop, just focus on the left-hand loop. How many currents? The same current passing through R1, the diode R2, isn't it?
yes.
So I can just call this current I or ID, whatever. IR1 minus 0.7 minus I times R2 plus 5 equals 0. You know the value of R1 and R2. R1 4.7 kilo ohm, which is 4700 ohm. R2 is 2.2 kilo ohm, 2200 ohm. What is the only unknown variable in this equation?
I.
I. So let's find I. I will be 10 plus 5 minus 0.7, that thing divided by 2 resistors in series. Let's calculate I. My answer is 2.07 milliamp. Please correct me if I do something wrong. Sometimes I make wrong calculation. Do you get 2.7 milliamp or 7? So waiting for you to confirm the value of I.
Same value.
Same value. Once you know I, if I ask you now, find out V1. Can you find? And also find out V2. Can you find it? I think you can find, definitely. So is silicon here, Miss Silicon?
Yes, teacher.
Can you find V1? Calculate V1, please. And Mr. Wisalut. Mr. Wisalut. Or is it Wisalat? 611-7430. Yu Cheng,
Yeah, yes, teacher. Yes.
please calculate V2.
Okay, wait a minute.
Okay. V1 you can find by Ohm's law, the current times R1. Simple. I'm writing the answer as well. See if your values are same as this. Silicon and Yu Cheng, are you done? Has anyone else calculated V1 and V2?
Yes, I got nearly the same.
Yeah, it depends on how many digits you take, but if you round up, it's going to be like this.
Yes, that is true.
So you can verify this equation now. The first equation I wrote, 10 minus 9.74 minus 0.7 minus 4.56 and then plus 5. If you put this in calculator, you'll get 0. The loop equation is satisfied, is correct. The last part of this problem, Sheshehan,
Yes, Ajahn.
I will ask you to find this thing you see in the screen. I will point it out. V out. What is V out?
V out is V1, Ajahn.
Is it?
I think so.
Okay. Give you a few more moments to think. V out you can take by two ways, because here is the ground, here is the ground. If you put an output voltage probe here, the plus probe will go to this point, the minus probe will go to the ground, which means V out is measured for the whole node, the last branch. It is V2 plus E2, which means this voltage plus this voltage. V2 you have a positive sign, E2 is a negative sign. You get 4.56 minus 5. So V out is actually measured from, let me draw an arrow. V out. V out is from the top of the node to the bottom. This is V out. You're going to get a negative voltage if you put with the probe. 4.56 minus 5, how much is it? It is negative 0.44 volts. There is a second way of finding V out. What is that? This point, the green arrow, and this point, they are the same node. So V out is the voltage drop from beginning all the way to the end of silicon. Now you calculate 10 minus 9.74 minus 0.7. What will you get? You will still get negative 0.44. That's the answer for V out if you are measuring. It doesn't mean that the diode is off. It's just where you put the probe. You are given circuits in the exam problem. You have to look. Where is V1 taken? Where is V2 taken? Where is V out taken? Different problems have different reference points. So you have to look at the reference point. Because this is 4.56, this is negative 5 from top to bottom. When you add, you get a net negative voltage for the output. But according to the left-hand loop, the condition is perfectly satisfied for the diode to turn on. That's why the diode is on. Any questions about this one? I have a few more for quick practice today. Okay, let's turn off this. Let's call the first circuit circuit A. The second circuit, let's call it circuit B. The third circuit we'll call circuit C. Is Patampong is here? Okay, Patampong.
Yes.
6135113. I will give you the circuit A to tell us what is the out in this circuit. What is the output voltage? Okay. Is the diode on or off? Tell me. First question.
It is on.
It is on. You are right. It is on. Absolutely correct. Plus 10 with the plus side, anode side. So you need at least 0.7, 0.3 or 1.2. It will turn on. After it turns on, which you said correctly, what is VD? What is the value of VD?
0.7.
Now it's not 0.7, it will be 0. Why 0? Because I did not mention to you. I did not say it is silicon or germanium. When I don't say the material, you will think you have to take it as ideal diode. So the ideal diode is like a short circuit. What is the voltage of short circuit? Short circuit voltage closed switch is 0. Once you tell me the loop is, it is on, the loop is closed, isn't it? Current can flow. Apply the KVL now. What is the KVL equation? 10 minus VD minus V out. VR is same as V out. V out is taken here. Across R, parallel node. 10 minus VD minus V out equals 0. So what is V out? VD is 0. We told VD is 0.
Minus 10.
Minus 10? V out is minus 10 or plus 10? It will be plus 10 from the equation. 10 V out equals 10 minus 0. 10 minus VD. So V out is 10.
Okay.
Kung Su, are you here?
Yes, sir.
Let's go to circuit B in this case. Your final goal is to find the output voltage. Now tell me, looking at the circuit and the arrangement, is the diode on or off?
On.
Is the diode forward biased or reverse biased?
It is reverse bias.
Reverse bias, because plus, but right now you have cathode minus. The diode is not on. It is off.
Diode is on.
Off, open switch. No current flows. So what is V out?
0.
0. Yes. V out is same as VR. Same node, parallel node. When there is no current, what is VR? Ohm's law. I times R. I is 0. Therefore V out is 0. Martin,
Yes, Ajahn.
circuit C for you. What are we looking at? We are looking at a circuit with two parallel diodes. Tell me what's going on. Let's call it diode 1. This is diode 2. Looking at the input voltage, polarity, and the diode arrangement, what is the status of diode 1, on or off? Is diode 1 on because it is forward bias, right? Plus with plus, minus with minus. Once the diode is on, what can we tell about the diode? Closed switch, open switch?
Open switch.
Open?
Close switch ครับ
Conducting, closed switch. So what is the voltage across this diode now? I did not mention the material. Ideal diode, what is the voltage when it's conducting?
10.
Once the diode is on, what is the voltage of the diode? It is 0. Short circuit voltage is 0. It becomes a short. Ideal diode becomes a short. It will be 0. Okay. Let's go to the second diode. Is the second diode on or off?
On ครับ
How is it possible that the both diode is on? Because they are opposite of each other.
So off ครับ
Do you understand the forward bias and reverse bias case? This diode is in forward bias, and this diode polarity is like this. So second diode, with respect to the input voltage polarity, the second diode is off. Off is open switch, which means the second branch there is really nothing going on. In the middle branch, this one here. Now if you put a voltage probe here, V out, which is same parallel node, what will you get? What voltage will you see?
0.
0 volts. Your final answer is correct. You will see this one you can ignore because there is no current going on here. This one, you will sense the polarity and voltage of this one. V out will be 0. It is not 10, it is 0. Now, if I gave you the silicon diode, what will be the value of V out?
0.7.
Yes, at that moment you would see 0.7 if I mention that it is silicon diode. So practice circuits like this. I will also give you homework at the end of this chapter. There you can also see some problems where you can do homeworks like this. It's now 2:50 for today's lesson plan. We are complete. The next one is about some diode application like half-wave full-wave rectifier using different types of diode circuits. And following that, we will move on to Zener. Zener diode, the details of Zener diode, how it operates. I would now like to call for the attendance. So please, everyone, respond when I call. Balan, Tirawut,
ครับอาจารย์
Napatra is here.
Yes.
Pakong,
Yes.
Rajay,
Yes, Ajahn.
Tonikan is here. Michelle was here. Phil here. Silicon is here. Visalut is here.
Yes ครับ
Yu Cheng, Sheshehan also here. Patompong also here. Kung Su and Martin, you both answer. So you are here. Korawit. Korawit. 6211548. Pichayut.
Yes. Thank you.
Pichayut is here.
Yes.
Kolawit is here. Pichayut is here.